Hello everyone. I'm going to start video 1 lecture for chapter 8, Metamorphism and Metamorphic Rocks. The term metamorphism means to change form. This is done by changes in temperature, pressure, or the introduction of hot ion-rich fluids. Textures often change during metamorphism, as well as mineralogy. The rock from which a metamorphic rock forms is called the parent, or sometimes it's called the protolith. And these can be igneous, sedimentary, or another metamorphic rock that simply gets re-metamorphosed. There are different grades of metamorphism: low, intermediate, and high-grade metamorphism. In this figure, we're looking at the sedimentary rock shale in A here. Shale is made up of clay minerals. If we take that shale and metamorphose it just to a low-grade situation, that shale becomes a metamorphic rock we call a slate. That was not a very good circle. And no longer is the clay stable as a mineral. Now we get mica and chlorite that are stable. So here we've changed the minerals. In B, we have an igneous rock, if you remember, a granite and a diorite. This is an in-between, a granodiorite. And under high-grade metamorphism and differential stress, what happens is you get a folded metamorphic rock called a gneiss. Gneiss is spelled G-N-E-I-S-S. In this rock, you get an actual banding of the light and dark silicate minerals. So I mentioned metamorphic grade. It's just a change in conditions, and you can start from low and go to intermediate and finally end up at high-grade metamorphism. Please keep in mind that when a rock is metamorphosed, it is a solid. It does not melt. If it melts, it's not metamorphic, it's igneous. Here's a figure showing the progression from the sedimentary world, which occurs at temperatures under 200 degrees Celsius. Then between 200 and 700 degrees Celsius, you're in your region of metamorphism. And above about 700 degrees, rocks begin to melt, and you go back into your igneous rocks. So sedimentary rocks form at or near the Earth's surface. Below that zone is metamorphism, and below that, when the rocks completely melt, we are in the zone of igneous rocks. What causes metamorphism? What is the driving mechanism? Well, there are several actually, and we'll start with heat. It's the most important agent, and it is important because it provides energy for chemical reactions to occur. Recrystallization of minerals also occur, and you can get recrystallization from small grains into larger grains, or you can get actually new, more stable minerals at the new conditions forming. Where does the heat come from? Well, heat comes from within the Earth itself, from when the Earth formed 4.5 billion years ago, as well as from the radioactive decay of isotopes in the Earth. Your book is referring to this as the geothermal gradient. As you get deeper in the Earth, temperature increases, about 25 degrees Celsius per kilometer depth. It increases because of the heat left over from the original formation of the Earth, as well as heat from radioactive decay of elements. So I did a modification here for two sources of heat. I put due to leftover heat during Earth's formation and radioactive decay of elements. I think that better defines it. Also, we have magma that intrudes into the Earth's crust and provides heat as well. These dashed white lines are showing the Earth's geothermal gradient. Notice at 300 degrees, and then we go to 6, 9, and 1200 degrees Celsius, where there is a subduction zone, the geothermal gradient gets drugged down into the subduction zone because this downgoing slab is cold, so it's pulling that cooler rock and cooling down deeper in the earth. On the continent, we're showing the geothermal gradient and heating due to, in this case, igneous intrusions. So that provides heat. So magma moving up, differentiating into the upper crust causes an increase in the geothermal gradient. So these rocks right in this area could be metamorphosed by heat from this magma body, and we'll get into the type of metamorphism called contact metamorphism later in this chapter. On the back sides of mountain chains, back arc basins form, and you get an accumulation of very thick sediments, and the sediment on the bottom of the basin can become metamorphosed as it gets buried deeper and deeper. That would be a low-grade metamorphic condition. However, it is metamorphism. Another mechanism that drives metamorphism is pressure. The term confining pressure means pressure is applied in the same magnitude in all directions. The result of that is pore spaces being closed and the rock becoming more dense. Differential stress occurs when you have the forces in one direction being stronger than in the other directions. If you think of two continents colliding and the differential stress directions, what happens is it would be compressional, so that the rocks are squeezed like they are in a vise, and they get shortened in one direction and elongated perpendicular to the primary stress direction. High pressure, high temperature environments imply deep in the earth, all right? And rocks will not behave in a brittle fashion, but instead they flow, and we use the term ductile to describe that type of behavior. This figure is showing an example of strata under pressure. In this case, though, it's confining pressure. Pressure is equal in all directions. In this situation, in B, we have continent-continent collision, and so the primary stress directions are right and left, and you get a shortening in that direction, but an elongation perpendicular to the stress direction. In order to get this folding in the rock, you have to have differential stress. You will not get that folding if you have confining pressure or stress. This metamorphic rock is called a metaconglomerate. You can see that there was differential stress because the pebbles are stretched. We know the primary stress direction was top and bottom because the pebbles elongated perpendicular to maximum stress direction. So this is ductile behavior. Here's another example of a road cut showing the folding in the rock that implies differential stress and also implies that this occurred deep in the earth where the rock behaved ductily. In addition, you see these fractures. That's brittle behavior in the rock. And that would occur after the rock was uplifted near the Earth's surface and stress was applied. It behaved in a brittle fashion, like a piece of chalk being dropped on the concrete, because it is colder near the Earth's surface. The last mechanism of metamorphism is chemically active fluids. This is hot, ion-rich fluids, what we call hydrothermal solutions. with the presence of hydrothermal solutions, the ions can move around. And so this aids in recrystallization of the minerals that are there. It can also completely change the chemical composition of the rock as well. So I want to wrap this video 1 up for chapter 8 with this last slide talking about the importance of the parent. Most metamorphic rocks have the same overall chemical composition as the parent. They may have lost or gained some water or carbon dioxide, for example, but overall the chemical composition remains the same. And what minerals make up the rock determines the degree to which each metamorphic agent causes change. In our next video, we're going to introduce some textures for metamorphic rocks and continue on with different types of metamorphism as well.